Hello, it's Dr. Daystorms, and in this chapter we're going to start to talk about quantum theory and the duality of light in particular. And so this is complete change from the thermochemistry that we've been doing in the last week or so. The goals for this discussion right now is to go over waves and the terminology used with waves, such as frequency and wavelength and amplitude, and also start to discuss energy in a different form. We've talked about energy with respect to heat and work, but now let's talk about energy with respect to the waves, with wavelength and frequency. And we're going to discuss the contributions of Einstein and Planck. So, first, to understand the electronic structure of atoms, so the way that the electrons work, you have to really understand the nature of what's called electromagnetic radiation, which sounds really scary. But in reality, this is everything from visible light to X-rays to radio waves, microwaves, and they're all related. And some of the terminology that's going to be used has to do with wavelength, amplitude, and frequency. So the distance between corresponding points on adjacent waves is called wavelength, and it's denoted with the symbol lambda. This is a lambda symbol. And the wavelength itself, these are called, these are crests, and this is a trough. So you can either go from crest to crest or trough to trough. You have to be careful. If you hit the line, you'd want to go from this point on the line to that point on the line. Okay, and so the units for wavelength, we're going to be discussing it in nanometers, or some form of meter, but we're talking about really, really tiny distances typically, unless you're talking about something large like a radio wave. Now, the number of waves passing a given point is given is done in cycles per unit time, and that's the frequency. Okay, and so with frequency here, they use different units. Okay, so when we're talking about, literally they give a known distance and they just count the number of times a wave travels within that distance, and it's going to be the number of cycles per unit time. So usually we're talking about inverse seconds, and one inverse second is actually equal to a hertz. And so if you have the old-fashioned radio dials where it would say like 260 megahertz, then, or not 260, be like 560 megahertz, then that they really were talking about the frequency of that radio wave. And if you have waves traveling at the same velocity, the longer the wavelength, the smaller the frequency, which should make sense. So if we look at this instance here, we have more. These are small wavelengths, but they travel many more times in that same length. And so therefore, the wavelength and the frequency has to be inversely proportional. Whereas we have a much larger wavelength here, but the frequency is much smaller. I've already mentioned this term, electromagnetic radiation. And so all electromagnetic radiation can travel at the speed of light, which speed of light in a vacuum is roughly 3.00 times 10 to the power 8 meters per second. And that's given that's a constant, and that's given the letter C. Now, since wavelength and frequency are inversely proportional, they always have to equal C. And so we get this equation of C is equal to lambda times nu, which I forgot to point that out, but this frequency here, this is frequency, and that's not the letter V, that's the Greek letter nu. So it's lambda nu is equal to C. So therefore, they are inversely proportional. If nu is, I was about to say V, if nu is large, then the wavelength has to be decreasing, and vice versa. That's why they're called inversely proportional. Now you may recognize or you should recognize, many of these forms of radiation. We have our X-rays, gamma rays. The gamma rays are at the far end, so they have very, very small wavelengths, so therefore they're going to have very, very high frequencies. Then we have our UV and our visible light. So this is what our eyes perceive, and it's a very limited portion of the electromagnetic spectrum. Okay, then we have our IR, the microwaves, and then the radio waves, which those are literally related to the radio waves that we hear, we listen to. So let's work an example. So the wavelength of a green light perceived by our eye is 540 nanometers. Calculate its frequency. So let's see, how do we go about working this? Well, remember, the speed of light is equal to lambda nu. We're given lambda and c is a constant. So therefore, the frequency is going to be equal to c divided by lambda. Now, the one thing to keep in mind is lambda in this instance is given in nanometers, and we need to convert that to meters. Okay, because c is a constant, and c is a constant of 3.00 times 10 to the power 8 meters per second. So let's convert 540 nanometers into meters. And if you remember, I'm not going to skip any step, but 1 meter is equal to 1 times 10 to the power 9 nanometers. So therefore, 540 nanometers is equal to 5.4 times 10 to the minus 7 meters. So now let's plug and chug. We have 3.00 times 10 to the power 8 meters per second. We divide that by 5.40 times 10 to the power minus 7 meters. Please note, let's see if this makes sense. Meters cancel and meters cancel, so the only unit that we're left is with this is inverse seconds, which is true. Yeah, let me move that over. That's the unit, inverse seconds, or also known as a hertz. So let's put this into our handy-dandy calculator. 3 times 10 to the power 8. Please make sure you know how to use your calculator correctly before the exam. Divided by 5.4 times 10 to the minus 7. You're going to get a very large number. This is 5.55 times 10 to the power 14 inverse seconds, which if you wanted to use the hertz, if inverse seconds kind of bothers you, you can say that's 5.55 times 10 to the power 14 hertzes. Now, the wave nature of light doesn't explain how the object glows whenever its temperature increases. So you've seen like molten lava or molten metals, or even if the radiation, whenever you heat the burners on the old electric burners on the stove and how they glow. So Max Planck explained, he explains that this energy comes in these packets called quanta, and the singular version of quanta is quantum. So these are really small packets of energy that can be given off by light. Einstein actually used this assumption to explain what it's called the photoelectric effect. So we can see here that you have some radiant energy. It comes and it strikes the metal surface, and some electrons can be given off. Okay? And you can actually pick this up. So the reason why this is important is now we can quantify the frequency in terms of energy. So now we can have that energy is related to Planck's constant, which is a ridiculously small number, 6.63, or some books will say 6.626, times 10 to the minus 34 joule seconds in frequency. So why this is so important is it now relates energy to frequency to wavelength. So now we can actually figure out the energy of a light. So how is that possible? Well, let's think this through. If, or since, E is equal to H times nu, and we have C is equal to lambda nu, we can now go ahead and solve for nu. That's the same thing as saying nu is equal to C times lambda. So if you know the wavelength of a light, you can plug this value of nu into the energy equation. And so now we have E is equal to H, which is Planck's constant, times the speed of light divided by wavelength. So we can see that as the wavelength increases, energy will decrease. They are inversely proportional. Whereas as frequency increases, energy increases. So to summarize this, is if you know the wavelength of light, you can calculate the energy in one photon. A photon is like a packet or a little amount of light that's given off, the smallest amount that's given off. Okay, so that's the amount of energy given off per photon of light. So let's do another example. Okay, in this example, we're going to calculate the energy given off by a photon of orange light, given that it has a wavelength of 680 nanometers. Okay, so let's just talk our way through what we know. So we are only given wavelength. Whoops, let's use a thinner pen. We have wavelength is equal to 680 nanometers. And we need to convert that to meters. So if you take 680 nanometers, we divide that by 10 to the power 9 nanometers for every 1 meter, you're going to get 6.80 times 10 to the power minus 7. Whoops, sorry about that. Six 6.8 times 10 to the power minus 7 meters. Sorry about that. Okay, we also know that E is equal to H nu, and remember C is equal to lambda nu. So therefore, we can say that nu is equal to C over lambda. We're going to plug that into this first equation, and we'll be given the fact that E is equal to H times C divided by lambda. Now, you have to look to see what H is. H is a constant and C is a constant. So H is equal to 6.63 times 10 to the minus 34 joule times seconds. And C is equal to 3.00 times 10 to the power 8 meters per second. So now let's calculate, and this is energy for a single photon. So let's calculate the energy is equal to, we stick in H, 6.63 times 10 to the power minus 34 joule seconds times C, which I'm just for space, I'm going to say it's just 3, but it's really 3.00 times 10 to the power 8 meters per second. So notice we have seconds cancel and seconds cancel. And we divide that by lambda in meters, which is 6.80 times 10 to the power minus 7 meters. So we have a meters on the bottom and meters on the top. So the only unit left is joules, which is an energy unit. So now we just plug and chug. So the energy of a single photon is going to be equal to 6.63 times 10 to the power negative 34, times that by 3 times 10 to the power 8, divide that by 6.8 times 10 to the minus 7, and we get 2.93 3 times 10 to the power minus 19 joules. So that's our final answer. Which, it's not a lot of energy, but a photon of light is a very, very small amount. So let's review, let's review what we've gone through so far. We talked about the relationship between frequency and wavelength. And remember, it's inversely proportional because they have to equal the speed of light in a vacuum. We also talked about the relationship of energy of light, of a photon of light, with wavelength and frequency, because the energy is equal to Planck's constant times the frequency, which is the same thing as saying Planck's constant times the speed of light divided by the wavelength. So energy is inversely proportional to wavelength and directly proportional to frequency. Hopefully this has helped explain a little bit about the nature of light and energy.